This is a solutions video to my Honors Physics Collision worksheet. We have number 32. It's an example of an explosion. We have two ice skaters. They stand at rest, so their initial momentum is 0. And then they push off from one another, and one goes to the right, one goes to the left. And so we'll draw a quick picture and label. I'll call this number 1. This is 2. This one has a velocity of, well, they said, let's see, what do they say? When they push off each other, the 45 kilogram skater acquires a speed of 0.62. I'll say that goes to the left, 0.62 meters per second. That's a negative. That's velocity initial 1. We want to know the other skater's mass. So hold on, this is mass equals 45 kilograms. This is mass 1. Mass 2 equals question mark. This skater will take off to the right with a positive 0.89 meters per second. So momentum is conserved. So momentum initial of the system has to equal momentum final of the system. The system consists of two objects. This is momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. Both of these initial momentums are 0 because their velocities are 0. So now I have 0 equals the momentum initial of 1, which is the mass of 1, m1, velocity 1 final, plus m2, velocity 2 final. What do I know? I know mass 1. I know the final velocity of mass 1. I know velocity 2. What do I not know? This is what I'm looking for, mass 2. So I have everything I need to solve for mass 2. I'll rearrange that equation, and I will say that mass 2 equals minus m1 v1 final divided by v2 final. And now I'll plug in numbers, and that is mass 1 is a positive 45 kilograms. There's a negative there. The velocity of the original, the final velocity, this is final. This is final 2. The final velocity of mass 1 is negative 0.62 divided by the final velocity of mass 2 is positive 0.89 meters per second. Negative times a negative, that's good. I want a positive number for mass, and I get 31.3 kilograms. Okay. I got an astronaut holds onto a satellite. Both are at rest. So here's my astronaut holding my satellite. They're both initially at rest. I'll call this object 1, object 2. The mass of the satellite is 1,200 kilograms. M1 is 92 kilograms. The astronaut pushes the satellite, given it a speed of 0.14 meters per second, directly away from the shuttle. So here's the shuttle, because I'm pushing it away from the shuttle. The astronaut comes in contact. This time is equal to 7.5 seconds. What is the distance away that the astronaut is? So we can use conservation of momentum to find the astronaut's velocity. If I know the velocity of the astronaut after it pushes away, since I know the time, I can find its distance it traveled in 7.5 seconds. So initial momentum of the system has to equal the final momentum of the system. The system is equal to the astronaut and the satellite. both of the astronaut and the satellite are at zero velocity initially. So that's zero initial momentum. So the initial zero has to equal the final of the astronaut momentum plus the final of the um, satellite, final of satellite. So zero equals mass 1 times velocity final 1 plus mass 2 times velocity final 2. What do we know? Well, we know velocity of final 2. We know both masses, and what we're looking for is this velocity after it pushed. So I can find that velocity. So V final 1 equals negative m2 V final 2 divided by mass 1. And we find that to be negative 1.8 meters per second if you plug in the numbers. I'll go ahead and show those numbers just real quick. That should be negative mass 2, 1200 times velocity final 2, 0.14 divided by mass 1, 92, and that will equal negative 1.8 meters per second. Makes sense that that velocity is negative because there is the velocity final of 1 to the left, as I've shown it. So we know the definition of velocity. Velocity's definition is change in x over change in time. They told me the time it takes is 7.5 seconds. So if I want delta x, I will rearrange that for delta x, and that will be equal to negative 1.8 meters per second times the time, which is 7.5 seconds. Since I called left negative, the displacement is in the negative direction, and that will equal negative 13.5 meters. So they asked for the distance. Distance is a scalar, so distance equals 13.5 meters. It moved 13.5 meters to the left. Number 40. We have a lumberjack stands on a 1,200 kilogram log in a pool of water. So I have this log, and I have, we'll say the shore is over here. This guy is standing on the log. They'll call him object 1 and this object 2. The lumberjack starts jogging. So now initially the velocity initial of 1 equals 0, velocity initial of 2 equals 0. We know mass 1 equals 94 kilograms. Mass 2 equals 1,200 kilograms. Then sometime later, this guy starts to jog to the right, so that's velocity 1 final. What's going to happen is the log will start moving to the left, and this is water. At least how I've drawn it. Okay. If the lumberjack's relative speed to the shore, that just is 2.2 meters. What is the log speed? So it'll be a negative number as I've drawn it because I'll assume right is positive. But we'll just drop the negative since speed is the magnitude of the velocity. This is a conservation of momentum. Since it's on water, there's no outside friction. Initial momentum of the system has to equal the final momentum of the system. The initial momentum is 0 because both velocities are 0. So we have the final momentum of the lumberjack plus the final momentum of the log. And what are we looking for? We're looking for the speed of the log, and that would be this V2 final. And I know everything else. Mass 1, mass 1, mass 2, mass 2, velocity final 2, velocity final 2. I'm sorry, velocity final 1. So I'm looking for V final 2. V final 2 equals the negative M1 V final 1 divided by M2, which is equal to 94 kilograms times V final 1, which is positive 2.2 as I've drawn it, divided by the mass of 2, which is the log, which is 1,200. So V final 2 is equal to negative 0.17 meters per second, and the speed of that is equal to 0.17 meters per second. To the left. Another ice skater problem. Ice skaters are at rest on a frictionless surface. That's not what excuse me real quick. Oh, we already did this. Looks like it. Did it reprint that one? Or is that another one? I'm going to jump to number 44. I'm going to eliminate those two problems from this worksheet. Okay. All right. A 1.35 kilogram block of wood is at rest on a smooth table. Okay. A 0.015 kilogram bullet moves horizontally with a speed of 715 meters per second and embeds itself with the block. What is the speed of the bullet block system after it collides? So here is the block. I'll call this 1. I'll call this object 2. I know that mass 1, mass 2, mass 1 is 0.0105, mass 2 is 1.35 kilograms. After the collision, the bullet is inside the block. So this is after. Velocity equals question mark. The velocity initial of 1 is 715 meters per second. The velocity initial of 2 is 0. The mass of this block, this is M1 plus M2. So we'd have to add that. That'd be 715.0105 kilograms. And velocity final equals question mark. This is a collision, so initial momentum of the system has to equal the final momentum of the system. The initial momentum of the bullet is mass 1 v1 initial. The initial momentum of the block is 0. It has 0 velocity. The final momentum is the two masses added together, because there's only one object, times v final of the 1, 2 object. I'm looking for that speed, so I will rearrange that, and I will get m1 v1 initial over the total mass of the block bullet system. So mass 1, 0.0105 times velocity 1, 715 meters per second, times the total mass, 715.0105 kilograms. I don't have the answer, so I got to get my calculator real quick. Assuming I don't do a calculator error, which I do on occasions, I get 0.0105 times 715 divided by 715.0105. I get the velocity of the block mass or bullet system to be 0.099 meters per second. That's to the right. I'll just round that up to 0.101 meters per second. Seems pretty small. Double check again. 0.0105 times 715 divided by 715.0105. Still get 0.01. Okay, so the reason why that velocity is so small is the block's mass is substantially larger than the bullet's mass, 1.35 divided by, let's, 0.0, I'll just tell you in fractions, divided by 1.35. It's only, the block is essentially 99.3% of the total system's mass. So the block is huge compared to the bullet. All right, we have number 45. We got a 1,200 kilogram car moving at 2.5 meters per second. Is struck from behind from a truck. There's my truck. It's moving at 6.2. I'll call that 1 equals 6.2 meters per second. This has an initial velocity. This is object 2. This is 1. Velocity 2 is 2.5 meters per second. Mass of the car is 1,200 kilograms. Mass of the truck is 2,600 kilograms. They stick together. So this is after the collision. I've got the truck and the car stuck together. So this is mass 1 plus mass 2. That's only one object. And we want to know what is their speed. This is a conservation of momentum problem. Momentum of the initial of the system has to equal final of the system. Momentum initial of the system is m1v1 initial plus m2v2 initial equals the one object, total mass is the two masses added, times the final velocity of this 1, 2 object. So now what am I looking for? I'm looking for the final velocity. I have mass 2 and 1 known, and I also know the velocities of the objects originally. So I know everything in green. I don't know the object in yellow. So I will rearrange this equation for the one that I don't know. I will divide both sides by the sums of the mass. Don't make a calculator error. You need to put those parentheses around that M1, M2, or add them up separately. And so mass 1 is 2,600 times 6.2 plus 1,200 times 2.5 divided by 26 plus, that'll be 3,800. That would be the total mass of the system. So let's calculate that real quick. Times 6.2 plus 1,200 times 2.5, enter. Now I'll divide by 3,800. I got the velocity of the object stuck together at 5.03 meters per second. That's positive because it's to the right. Okay. Number 55, a cart of mass 0.12 kilogram moves with a speed of 0.45 meters per second on a frictionless track, collides with an identical cart that's stationary. They stick together, similar to what we just did. What is the initial kinetic energy and what is the final kinetic energy of the system? I'm going to hold off on this and I'll make another video. These are related to energies and the students have not learned that yet. So that's what I got.